What page is this? 42, and we're on question 16. Okay, we need to talk about this formula here. Okay? If there's no average in there, well, this formula here. This average velocity formula is typical of uniform motion, okay? Now, you see V average. So like if I'm a sprinter, Usain Bolt, right? I start off at 0 speed and I end up going pretty fast near the end, right? I have a whole bunch of different speeds the whole way, right? But let's say Mr. Bolt is doing the 100-meter dash. He does the 100-meter dash, D, in like 9.7 seconds, okay? So this formula here will only calculate his average velocity. He is accelerating the whole time, right? He's speeding up. This only gives you the average, not the instantaneous, okay? That's important to note, okay? Now I told you that you only use this formula if it's uniform. Remember I said that? If you want to use this formula for an accelerating object, you can, but you have to keep in mind that the average is this formula here. Okay? And this is on your formula sheet. I'll point to it on your formula sheet. So, formula sheet, it looks like this. Oops. Got D equals Vf plus Vi over 2 times T. Okay? So you can use this formula, but just keep in mind that, so you can use this formula for acceleration, for an accelerated object, but you have to use the average. Okay? The graph would look like this. Okay, here's V, here's T. Some time interval from here to here. Okay, here's VI, here's VF. If you add those two things up and divide it by 2, that's like an average, right? Your final plus your initial divided by 2, it's going to put you right here in the middle. Okay? So that's your V average, right in the middle of that graph. And it happens at the half-time mark. I hope that makes sense. Okay, so Usain Bolt, imagine him. He starts off at what speed? He's in the sprinter blocks. What speed is he? 0. And then he's taking off. Maybe at 1 second he's going like 2 meters per second. And then at 2 seconds, maybe he's going like 5 meters per second. I don't know what the numbers would be, right? He's speeding up. At every moment, he has a different speed until the 100 meters is done and he stops the race, right? So he's always got these different speeds. What are those called? Starts with I. Those are your instantaneous speeds, right? But on average, he'll just be d over t, on average. On average, he's just d over t, maybe 100 meters divided by like 9.7 seconds or something, right? So when does he experience his average speed? Because remember, he starts off here. When does he experience the average? Right in the middle of the time interval. So at the half-time interval. Okay, so let's take a look at 16 and let's answer 16. Okay, a toy car is accelerating to the north. We have a VI, we have a VF in a time. Okay, we're using our formula above. I'll just jot down what I would use from my formula sheet. VF plus VI over 2 times T. This is on your formula sheet. You can make a little note if you'd like. I'm okay with that. On your formula sheet, please put a little arrow to this term and put V average. I'm okay with that if you put that onto your formula sheet. That term is the V average. Okay? So this question will be pretty self-explanatory at this point. 1 plus 7 over 2 times 3. Sorry, yeah, same thing, my bad. 7 plus 1. Oh, we're not searching for the displacement. We're just searching for the V average, right? So we're just trying to find this term in purple. I'll make it a little bit nicer, sorry. And we'll put it in the right order so that people with OCD are happy. 7 plus 1 over 2. Now, Jacqueline showed me some stuff on her calculator with this. She got 2 different answers. So when you look at this, is this, how would you put that in your calculator if it was harder numbers? You would use brackets. There's invisible brackets here. You must take care of that 7 plus 1 and then divide it by 2. So it's 8 divided by 2, which is 4. And the unit for average velocity would be meters per second. And which direction are we headed? Oh, it says we're headed north. Okay, so there's part A for you. Now, the instant in time that you experience the average velocity, we talked about that. It was the half-time mark. Okay. So here you are at 1, and then you get all the way to 7 on a VT graph. When do you experience the average? Well, that would be right here at 4. And it's the half-time mark. And the time interval was 3 seconds, right? So half of 3, 1.5 seconds. Okay, so in general, like if you're writing an exam, you guys, this VDT formula, this one here, typically you only go to it for uniform motion. And if you have accelerated motion, you stick with this kinematics equation and all the other kinematics equations. There's 6 of them? 5 of them. Okay? So on your formula sheet, oh, lovely. Top left, uniform motion, okay? The other 6, kinematics, acceleration. Okay, the next one I want to do, I think, now that my book has fallen, let's find it. La-di-da. Oh, I think Adel wanted me to do question 4, so we've got to back up. This was on the quiz as well. So he said you wanted me to cover one of these. This was in your homework. So it says vector arrows can be used to represent velocity and acceleration. A ball speeds up at a rate of 3 meters per second squared as it moves from left to right. So if it's moving from left to right, it already has a velocity vector this direction, left to right. And it says it is speeding up. So they also want you to draw the acceleration vector. If it's speeding up, your acceleration vector will be in the same direction. Now, just a word on vectors. The size of the arrow is supposed to give an indication of the magnitude. Okay? At this point, I'm just worried about the direction. If you get the direction, okay, it's fine. Okay? But it says the velocity is 6 and the acceleration is 3. So like this should be twice as large. See how this is a 6 and this is a 3? This velocity should be twice as large as this acceleration. So the arrows give a relative idea of the magnitudes. Okay? Now if it's slowing down, this was on the quiz, you just have it in the opposite direction. This magnitude is 3, this magnitude is 6. So if that's 6, 3 would be half of that. Here's your acceleration, here's your velocity. And these other arrows are confusing, so let's get them out of there. Any questions on drawing the vectors? We're going to spend a lot more time on this when we get to the 2D vectors. So, yes?
So when you put it into calculate, do you put
You can, but make sure those two numbers have a bracket around them first. Yeah. Right, exactly. So invisible brackets. Okay, so hopefully you had a chance to do 10 and 11. I really like those ones because you have to have the sign is important. Okay, so the homework was up to 15. I just showed you 16. So 16 will be a lot like 17. So I'll leave 17 for you guys, and I'm going to do 18 with you guys. 18's kind of nasty. Okay, so let's read 18 together. Let's highlight some key information, and let's see if we can come up with some strategies to make this less stressful. Okay, so pressing on the brake slows the car down from a speed of 35 to 15. So let's just jot on there. What's the VF and the VI? Okay, we got our VI and we got our VF. What's next to that is T. So right there, what can you solve for? Do it. Let's do that right now. Acceleration equals VF minus VI over T. 15 minus 35 over 7.5. This is what we've been talking about with these invisible brackets, right? You absolutely do 15 minus 35 first. I get negative 20. Divide that by 7.5, and I got negative 2.6 repeating. Now I'm going to keep that in my calculator for accuracy. Okay. So we got our A value. Now we can see what this question wants. Draw the acceleration vector and the velocity vector on the car below. Okay, so at this first moment in time, your velocity vector might look like this. This is for VI. Now, over in this moment of time, here's the car, just a box. Right, here's the car. Same car, just in a different moment of time, 3 seconds later. Your speed has gone down, right? So the magnitude has decreased, so your arrow, still pointing in the same direction, will be just smaller. Okay, just smaller. And there is your VF. Okay? And what would the acceleration vector be doing? Pointing the opposite direction because you're slowing down. And we solve for that, right? Negative 2.6. So if that bar represents 35, this is probably pretty small. There's the acceleration vector. And in another moment in time, that acceleration vector is still there. Okay? So you just imagine an object, which can be represented by a block, and you just draw acceleration arrows to the left and velocity arrows to the right, because you're driving to the right and slowing down.
If the key needed, for example, 1 centimeter is equals to maybe 10 meter per second, do you have to something like that? Is something like that needed?
I don't think so. Is the key needed? What?
Sometimes you gotta have to like velocity and acceleration, which is 2 different units. You know what you're doing?
These are all the same units, so meters and seconds.
Seconds quick. You need to have like.
Oh, the way I write it?
No. I'm saying like for example, I wrote this one, yeah. 1 centimeter is equals to 1 meter per second. Per second. So now this is 6 centimeters long, this is 3 centimeters. It's basically the same thing as you're saying, but do we have to indicate this?
No. No, you do not. It's just a relative idea. It doesn't have to be perfect. Yeah. So like, sorry guys, I just gotta clarify this for this student here. Okay, let's say, like, I'm pulling on this object this way, and I'm stronger than you. So you pull on it this way. So obviously it's going to go that way because I'm stronger. But it just so the person who's reading this can tell this is bigger than this. That's all that matters. Like, it doesn't have to be perfectly proportional. Does that make sense? I don't know. Okay, let's keep going. We got the A value. We've drawn the vectors. Now we want to determine the car's speed after a certain amount of time. So let's go for part B here. Now we have a time of 3 seconds. Okay, we have an initial velocity which was 35. And we have an A value of negative 2.6. So which formula could we use here? Determine the car's speed. So we need I feel like going after C would be a little bit easier. Determine how far the car has traveled in the first 3 seconds. VIT, because if you go to this one, VIT plus 1/2 AT squared, what are you missing? You don't have this, right? But you have VI, you have T, and you have A. So you could solve for displacement. So let's do that first. Like sometimes when I look at these questions A, B, C, I'm like why do I have to go in your order? But okay. But that's why I'm like, right off the bat, what did I do first? I looked at these. This is what I did first. So from these 3 things, what could I find? A. Now I have an extra part of the puzzle. Now that I have A, and and they also gave me this. This was a new value, 3 seconds. I can find the D for this. I can find displacement. So let's go ahead and solve for displacement. So we got 35, 3, plus a 1/2. A is negative 2.6 repeating. And like I would copy and paste that from my calculator. And T here is going to be 3 squared. So this should give us our displacement. I need a graphing calculator. What? Is that what we want? 35 times 3 plus 0.5 times a negative times 9. Okay, I got 93. And displacement. Oh, it just wants how far, so just a distance. Okay, so part C we've solved. So we can erase that, put a C. And if you look at part C, it says determine how far, so I didn't put any direction. Now let's go ahead and solve for part B. It says determine the car speed after 3 seconds. So that means VF. And this is a different VF, isn't it? No, because that's 7.5 seconds. Right? VI stays the same, good. What do we know? The distance after 3 seconds. So the distance after 3 seconds is 93. And we want the VF. And we know the A is negative 2.6. No, it says determine the car's speed after 3 seconds. The acceleration will always stay the same, this negative 2.6. That will never change. Yeah. And they gave us also a time. So we actually have a lot of information that we could use. A ton of information. Yeah, if you had a formula for the graph, for sure. Do you have a formula for the graph? We could do that. Here's a nice one though. VF square equals VI square plus 2AD. So all we would have to do is square root and solve for VF. Okay? So VI squared, 35 squared. 35 squared, 1225. And then this is going to be minus, because A is negative. So 2 times that 2.6 repeater, with it being negative, times this 93. So it ended up being like 496. I don't know if you guys got that. 1225 minus 496. Square root that bad boy. 27. Now, when I was doing this last year in my book, I actually did it a different way. I used another formula. So what I'm trying to demonstrate here with this problem is that there are multiple ways to get the same results. You just have to be mindful of what you have and what you want. And this is so true in your math and physics in high school, is if you can just identify what you have and what you want, and you pick the right formula and you can sub stuff in and do algebra, you should be generally okay. Alright, so I want you guys to finish the second section of questions in this. It is numbers 16 to 26. So I've already done 16 for you, and 18. So you need to try 17. I'll put this on the top. 17 to 26. And if you cannot get number 24, do not stress out. It's quite a hard question. So if you could do 17 to 26, and we'll talk about 24 tomorrow, that's cool. Please try 24 though. It is the hardest one in that group of questions. Okay, so you have the rest of the class to work. More questions? Well, you just keep going then. We're going to spend some more time on this tomorrow though.